Hey everyone, and welcome to today's Explainer. We're diving straight into the massive, hidden forces moving right beneath our feet. We walk around on the ground every single day, totally assuming it's solid, permanent, and just completely still. But the reality? Our planet is incredibly dynamic. It is constantly shifting, shaking, and erupting. Here's the 5-step journey we're taking today. Earth's moving plates, the origin of earthquakes, measuring the quakes, magma and lava formations, and finally, volcanic mountains and eruptions. Let's get into it. Section 1. Earth's moving plates. Okay, so to understand anything about earthquakes or volcanoes, we first have to completely change how we picture the Earth's surface. It's really not a single solid shell. Think of it more like a giant jigsaw puzzle that is in constant, extremely slow motion. And there are 3 distinct types of boundaries where these puzzle pieces, which we call plates, interact. First, we have divergent boundaries, where plates are pulling apart from each other. Next, transform boundaries, where plates are grinding and sliding right past one another. And finally, convergent boundaries, where plates are just crashing head-on together. This brings us to a massive key word for today: plate tectonics. This is the overarching theory that Earth's outer shell is divided into these moving plates. And the absolute key takeaway here is that those 3 boundaries we just talked about, they act as the engines for our planet's geography. When plates pull apart, they form these vast ocean ridges and deep rift valleys. But when they crash together, that immense pressure literally buckles the crust upwards, creating massive mountain ranges. Moving on to Section 2, the origin of earthquakes. So we know these massive plates are moving, but what actually happens when millions of tons of rock get stuck against each other as they try to move? Well, the answer lies in the elastic rebound theory. Picture holding a plastic ruler in your hands and slowly bending it. As you bend it, it accumulates energy, right? It deforms. But eventually, you reach a breaking point and snap. The ruler breaks, and your hands actually sting from that sudden vibration. The exact same thing happens with rocks on the borders of tectonic plates. They accumulate energy, they deform, and when they exceed their breaking point, they snap. That sudden release of accumulated energy blasts out in the form of intense vibrations. Let's build our vocabulary here with 2 critical terms you absolutely need to know. First is the hypocenter. This is the exact point deep within the Earth's lithosphere where those rocks snap. It's that deep, invisible origin point where the earthquake's elastic vibrations actually begin. And that is followed immediately by the epicenter. Now, when you watch the news after a quake, this is the word you always hear. The epicenter is simply the point on the Earth's surface located strictly on the vertical line straight up from the hypocenter. If we map this out, that point deep underground is your hypocenter, right on the fault line where the snap occurred. Follow that straight up to the surface and boom, there's your epicenter, usually right near a town or city. And those rings rippling outward, that's the energy moving in all directions. We call those vibrations seismic waves. Section 3. Measuring the quakes. Since we obviously can't see these waves traveling through solid rock underground, scientists capture and measure them using a really clever instrument called a seismograph. It looks simple, but it's brilliant. There's a heavy pen suspended by a spring. Because of its mass, when the ground starts shaking, that pen stays completely still. Instead, it's the base of the instrument and the rotating paper drum that move wildly beneath the stationary pen. That's what draws out the exact pattern of the Earth's movements. The paper readout it creates is called a seismogram. Let's decode these specific waves because they actually arrive in a very distinct order. First, you see the P waves, or primary waves. These are the fastest. They produce a compression motion and can travel through both solids and liquids. Next up are the S waves, or secondary waves. These are slower. They move in a shearing motion, and here's the catch. They can only travel through solids. Finally, when P and S waves reach the surface, they combine to create surface waves. And as you can tell by the massive spikes on the readout, surface waves are the most intense and are responsible for the vast majority of earthquake damage. Once we capture the waves, we have to grade the earthquake's strength. And we use 2 very different scales to do this. The Mercalli scale, or MCS, has 12 degrees and measures the visual, physical damage caused to buildings and people. The Richter scale, on the other hand, is a strictly mathematical, base 10 logarithmic scale. It measures pure magnitude, the absolute maximum amplitude of the Earth's movement. So simply put, Mercalli is about the physical damage you see, and Richter is about the raw energy released. Scientists use all this data to calculate real-world seismic risk for different territories. Risk is actually a math equation. It equals the seismic hazard multiplied by the exposure and the vulnerability of the area.
We can look at this color-coded map of Italy as a perfect example, objectively outlining zones of higher hazard in red and lower hazard in green. This kind of mapping is absolutely crucial for helping cities prepare their infrastructure.
Section 4, Magma and Lava Formations.
All right, let's shift our focus to the intense heat of the Earth's interior and talk about melted rock. Before we go any further, we have to establish a major terminology difference so you never confuse these two on a test. Magma is molten rock rich in minerals and gases that is trapped completely underground. Lava is simply magma that has breached the surface. Literally, the moment magma touches the outside air, it becomes lava. It's the exact same stuff, just in a different location. But, not all magma is created equal. Its chemical makeup completely dictates how a volcano will behave. Let's look at the percentage of silicon dioxide, or SiO2. Focus on the two extremes here. Acidic magma has over 65% SiO2. This makes it highly viscous, which is just a fancy word for thick and sticky, and it's relatively cooler, around 600 to 800 degrees Celsius. Basic magma, however, has only 45 to 52% SiO2. Because of this, basic magma is much hotter, well over 1,000 degrees, and it's highly fluid, kind of like warm honey.
Finally, Section 5, Volcanic Mountains and Eruptions.
Let's follow that magma's journey all the way up as it forcefully breaks through the surface. At the very bottom of a volcano, you have the magma chamber. Think of this as the underground fuel tank. When pressure builds, the magma travels up a central pipe called the conduit, and finally, it blasts out through the opening at the very top, which we call the crater. Now, how that magma escapes the crater depends entirely on the chemistry we just discussed. If a volcano is fueled by that hot, fluid basic magma, the gases can easily bubble out and escape. This results in an effusive eruption, gentle, steady, flowing rivers of lava. But if a volcano is fueled by that thick, sticky, acidic magma, gases get trapped inside it like a shaken soda bottle. The pressure builds and builds until it triggers a massive, violent, explosive eruption, blasting ash and rock miles into the sky. And actually, there's a third option. Sometimes magma never breaches the surface at all. It slowly cools deep underground to form massive solid rock structures in what we call an intrusive process. Believe it or not, these eruption styles completely dictate the actual shape of the mountain. Volcanoes with fluid, effusive eruptions build up slowly over time into wide, gently sloping mountains called shield volcanoes. The massive volcanoes of Hawaii are perfect examples of this. On the flip side, volcanoes with violent, explosive eruptions build up steep, layered peaks called stratovolcanoes. Famous European volcanoes like Vesuvius and Etna fall into this explosive category, often alternating between heavy explosions and lava flows. But that leaves us with a really interesting question. What happens when the spectacular eruption is finally over? Does the mountain just instantly go quiet? Well, no. The truth is, the Earth continues to breathe long after the visible red lava stops flowing. We call this post-eruption phase secondary volcanism. Even though the main eruption is over, there are still massive pockets of magma slowly cooling underground. If groundwater trickles down and touches this hot rock, it boils and shoots back up to the surface as intermittent jets of hot water, called geysers. You might also see fumarolas, which are hot acidic steam vents bursting from cracks in the ground, or mofets, which are low-temperature emissions of carbon dioxide gas. The Earth's plumbing system is still very much active. So we've traveled from deep tectonic plates, ridden the seismic waves of an earthquake, and followed magma straight out of an explosive crater. Next time you read about the ground trembling or you look up at a towering mountain peak, ask yourself, what invisible jigsaw puzzle piece deep underground created this? The forces might be hidden, but as we've seen today, their impact on our world is absolutely earth-shattering. Keep observing this incredibly dynamic planet around you, and I will catch you on the next explainer.